Hello and welcome to our next lecture. Today we're shifting gears and we start talking about the Fourier transform. The Fourier transform has a lot in common with the Laplace transform we just discussed. However, it is significantly different to warrant a separate discussion. As usual, things always start with the definitions. And the definition of the integral Fourier transform is very similar to the definition of the Laplace transform. I haven't talked about the existence of transforms in detail. The Laplace transform has its own prerequisites that are imposed on functions. Fourier transform requires the functions to be from L2. Suppose I have a function from L2. And this time I'm considering L2 on the whole real line. We define the integral Fourier transform, or just Fourier transform, as, and there's a script letter f of f, and it's a function of omega. Another notation that people often use if they put a little hat symbol on f as an integral from minus infinity to infinity of f of t against e to the minus I omega t dt. In this regard, the formula is very similar to the formula we have for the Laplace transform. The difference is that instead of s we have I omega, and instead of integrating from 0 to infinity we're integrating from minus infinity to infinity. Well, for the Laplace transform we assume that all of the functions are 0 for negative t, and therefore integrating from negative infinity to positive infinity was not really necessary. The Fourier transform doesn't make those assumptions, so the integration is done over the whole real line. Also, I'd like to point out that this is the same as an inner product of f of t with the function e to the positive I omega t. So why is this thing negative under the integral? Because, as I told you earlier, the inner product requires the second function to be complex conjugated, and the complex conjugate of e to the I omega t is e to the minus I omega t. I'd also point out that the definition I give you here must be understood within the context of improper integrals. The improper integrals are always computed as limits. And since there are two limits of integration that are both infinite, this is the limit that we have in place. We assume that the capital R is a number that specifies the interval from minus capital R to positive R, and we just integrate over a finite interval. Over a finite interval, pretty much any continuous or bounded function is going to be in L2. E to the minus I omega t is also a member of L2. And if the limits of those integrals exist, this is going to be the definition of the value of the Fourier transform at the frequency omega. Why did I say frequency omega? If you remember from any introduction to the complex numbers that you might have had before, like for example the one we do in the differential equations classes, you remember the Euler's formula. And the exponential functions of this form always break down into sines and cosines. Therefore, omega plays the role of frequency in these expressions. Another thing that I just want to throw at you, but I will not provide any details as to why it actually works. The function e to the I omega t is not a member of L2 from minus infinity to infinity. Therefore, computing the inner product that I just outlined here is not strictly a legitimate operation within L2. However, it does work and the limit always exists if the function f of t belongs to the L2 space. And the proof of that is very elaborate and requires understanding of the advanced real analysis, things like measures and the Lebesgue integration. This is way too much for our class. Well, I'm just going to say that things work the way they're supposed to work, and we should be happy with that. I would also like to make a remark, and it is really unfortunate that I have to make this remark. In different textbooks, in different contexts, the definitions of the Fourier transform differ. Some people define the Fourier transform with the factor 1 over square root of 2 pi in front of the integral. And we're going to see later why would some people want to do something like that. Sometimes the Fourier transform is defined with the factor 1 over 2 pi in front of the integral. An unfortunate consequence of all of this confusion is that the definition of the Fourier transform in Mathematica is different than the definition I'm giving you here. The definition I give you here is the mathematical definition that is accepted within the world of mathematicians. In engineering and physics, you might see different definitions of Fourier transform, but sometimes people go to the extreme and they actually change whether or not you put the minus sign right here on the Fourier transform or you put the minus sign on the inverse Fourier transform. As you can see, Mathematica does things its own way. Not only put the 1 over square root of 2 pi in front of the integral, it also puts the positive sign on the term e to the I omega t. This is not going to be a big obstacle for us, because the Fourier transform function also provides us a way to correct for any disagreement you might have about the definition. So for example, if I say that b is -1 and put a to be 1, then the Fourier transform performed with this function will agree with the definition that I gave you. Just like the Laplace transform, Fourier transform is invertible. But contrary to the case of the Laplace transform, Fourier transform has a formula for the inversion. And the formula is 1 over 2 pi, the integral from minus infinity to infinity. And we take the Fourier transform of my function, f hat of omega, and we integrate against e to the positive I omega t, but this time we integrate with respect to omega. It is now clear why sometimes people want the factor 1 over square root of 2 pi in front of the Fourier transform formula, because then the Fourier transform formula and the inverse Fourier transform formula will look almost identical to each other. The proof of this formula requires some mild application of the techniques you learn in your multivariable classes, and it is really not that difficult to show that this inverse transform formula actually works. You might be wondering, why didn't we have a formula for the inverse Laplace transform? Well, unlike Fourier transform, the inverse formula for the Laplace transform requires integration within a complex plane. And since we haven't spent any time talking about the integration of complex valued functions and what it means to integrate a function inside a complex plane, we didn't discuss the formula. But yes, the formula exists, and it is an integral formula of this kind, except that integration happens within the whole complex plane. Those of you who are interested are more than welcome to take complex analysis classes where the complex integration will be discussed in great detail. Let's look at a quick example and compute the Fourier transform of a simple function that does a step up at t equals a and step down at t equals b. Functions like that are called characteristic functions, hence the Greek letter chi used for this kind of functions. These characteristic functions are exactly 1 on the set and exactly 0 outside of the set. So this is a characteristic function for the set from a to b. Computing the Fourier transform of the function chi means performing integration from minus infinity to infinity of the function chi a comma b times e to the minus I omega t dt. Since the function chi is 0 outside of the interval a to b, this is the same as the integrating from a to b of e to the minus I omega t dt. Well, this is a simple integration. It's just 1 over minus I omega times the function e to the minus I omega t evaluated from a to b. So this is 1 over minus I omega times e to the I omega b minus 1 over minus I omega e to the I omega, forget about the minus I omega a. And here I'm going to re-express a and b as values that are on the same distance from the center of the interval a to b. So I can say that a is a plus b over 2, which is the center point, minus the half value of b minus a over 2. And b is a plus b over 2 plus b minus a over 2. You're going to see why I'm treating it this way, since both of the functions can be now written as products of exponential functions, and both of these functions will involve e to the minus I omega times a plus b over 2. I can factor it out. And what's inside is simply e to the minus I omega times b minus a over 2 minus e to the minus I omega times b minus a over 2. With a negative sign, we'll turn it into plus. And here's a little magic that the complex variables provide us. I know that sine of theta can be written as e to the I theta minus e to the minus I theta over 2i. Given this knowledge, I can convert this into e to the minus I omega times a plus b over 2 multiplied by 2, because I'm going to bring 2 in the bottom. I stays there, minus sign at the bottom of this fraction. When factored into this big parenthesis, we'll just switch the positions of the exponential functions, and I will get just sine of omega times b minus a over 2. Divided by omega. So this is sort of like a sine of x over x function, which has a name, sinc, for those of you who are familiar with it. In particular, if a and b are negative of each other, then the formula loses the exponential term, which becomes just e to the 0. So it simply becomes two b times sine of omega b over omega b. And this is true when omega is not 0. And when omega is 0, we know that this is converging to 1, and therefore it's just going to be 2b. Next, I'd like to discuss the properties of the Fourier transform and point out the similarities between the Fourier transform and the Laplace transform. Because Fourier transform is an integral operation, that means that this operation is linear. So if I'm applying a Fourier transform to a linear combination of two functions, then it's going to be the same as alpha 1 Fourier transform of the function f1 plus alpha 2 Fourier transform of the function f2. Since we're talking about functions from the space L2, each function has a norm, and the Fourier transform sort of preserves the norms. So the norm squared of f, which is the integral from minus infinity to infinity, absolute value of f squared dt, equals 1 over 2 pi the norm of the Fourier transform. Absolute value of f hat of omega squared d omega, which is 1 over 2 pi the norm of f hat squared. In a way, what this tells us, that the norm of the function is the amount of energy stored in the function. So if we talk about function of time f of t, and we talk about the Fourier transform f hat of omega, then both of those functions have a similar energy stored in them. Very often f hat of omega is called the spectrum of f, because, as I said, omega has a physical meaning of frequency. So f hat of omega has the physical meaning of the amplitude of the frequencies present inside the signal f. Just like in the case of Laplace transform, we can shift the functions and multiply them by exponential factors. So for example, if I want to compute a Fourier transform of a function f multiplied by an exponential factor, e to the I a t, then this is going to be an integral from minus infinity to infinity f of t multiplied by, and if I combine the exponential factors, I will get minus I omega t plus I a t dt. So this is going to be the same as integrating f of t against e to the minus I omega minus a t dt, which is going to be the same as the Fourier transform of the function f of t, instead shifted by a. So just like in the case of the Laplace transforms, multiplying by exponential factors gives us shifts in the Fourier transform, except that exponential factors are just a little bit different. What if I take a Fourier transform of a function that is shifted, and this time there is no requirement for a to be positive or negative? Well, this is the same as integrating f of t minus a e to the minus I omega t dt, which is the same as integrating, after a change of variable, I'll say tau is t minus a, t is therefore tau plus a, and dt and d tau are the same, and since we're integrating over the infinite real line, t and tau will also have the same limits of integration. So this is the same as integrating from minus infinity to infinity of f of tau multiplied by e to the minus I omega tau plus a d tau. So I get e to the minus I omega a outside of the integral, and the inside clearly can be seen as just a Fourier transform of the function that hasn't been shifted. The last property I want to consider today, the rest of the properties are saved for the next lecture, is the dilations. What if you have a Fourier transform of the function where the internal variable is multiplied by a constant? Here, c is not equal to 0, because when c is 0, f becomes constant, and the constant functions, unless it's a zero constant, are not members of L2. I'm going to consider this as a limit. As capital R goes to infinity, the integral from minus r to r of f of ct times e to the minus I omega t dt. And here I'm going to make a change of variables. I'm going to say that the variable tau is ct, therefore d tau is c times dt, and tau of capital R is just c times r, and tau of minus r is minus CR. And this is where things are becoming interesting. If C is positive, then there is no switch in the limits of integration that we will have to do later. If C is negative, we'll have to make a switch. So let's go ahead and break it into two cases. If C is positive, then this integral equals to the integral from minus CR to CR. And again, we take a limit as R goes to infinity. Inside, I have f of tau multiplied by e to the minus I omega. T is simply tau over c. And I put over c onto omega d tau times 1 over c. So this is simply 1 over c. And if we let r go to infinity, then this is just going to be the integral from minus infinity to infinity of f of tau times e to the minus I omega over c tau d tau. So it is simply 1 over c, the Fourier transform of f, but computed at omega over c. Alright, that was case 1. Case 2, if c is less than 0, let's just say c is minus absolute value of c. Then this is what we get. We get that the integral is going to be equal to the limit as r goes to infinity. It's going to integrate from absolute value of CR to the minus absolute value of c times r. We will have f of tau multiplied by e to the minus I omega of tau over c. And I'm just going to keep it c here because the sign here doesn't really matter. Times 1 over c, which is 1 over minus absolute value of c d tau, which is going to be the minus sign in the fraction 1 over minus absolute value of c will disappear when we flip the limits of integration. So this is still going to be the limit as r goes to infinity, 1 over absolute value of c, the integral from minus absolute value of CR to positive absolute value of CR, f of tau, e to the minus I omega over c tau d tau, which equals to 1 over absolute value of c, Fourier transform of f, computed at omega over c. If we combine these results, we get that the Fourier transform of f of ct of omega is the same as 1 over absolute value of c, because the absolute value of c, when c is negative, makes it positive, and when c is positive, makes it positive. The Fourier transform of f computed omega over c. In particular, when c is negative 1, the Fourier transform of f of minus t of omega is the same. So 1 over absolute value of negative 1 is 1, the same as the Fourier transform of f evaluated minus omega. For now, this is it for the properties. Let's consider a few examples. First example, I'll look at the function that behaves like 1 plus t on the interval from minus 1 to 0, and like a function 1 minus t on the interval from 0 to 1, and it's 0 everywhere else. So this is a little triangle from minus 1 to 1. How can we compute the Fourier transform of this? Well, we have to break the integral into two parts. And the part of the integral from 0 to 1 we will compute, and the part of the integral from minus 1 to 0, we're going to say that this is a mirror reflection of the other side of the function, and use the dilation property that I derived above. So let me compute the Fourier transform of the function 1 minus t on the interval of 0, 1. Well, this is going to be simply an integral from 0 to 1 of the function 1 minus t times e to the minus I omega t dt. The integration of this form is performed with integration by parts. I'd like to use Mathematica. So we're going to integrate the function 1 minus t times e to the power minus I is capital I in Mathematica. Omega is escape W escape. T we evaluate in terms of t from 0 to 1. Copying this expression, we get 1 minus e to the minus I omega divided by omega squared minus I over omega. For the Fourier transform of the function 1 plus t, evaluated in terms of chi from minus 1 to 0, well, since it's a mirror image of the Fourier transform that I just did here, this is going to be the Fourier transform with the omega replaced by minus omega. So it's going to be 1 minus I of minus omega over minus omega squared plus I over omega. When I add these together, I get that the Fourier transform of f is 1 over omega squared multiplied by 2 minus, and I have e to the I omega plus e to the minus I omega, and I over omega cancels out. So I'm going to add 2 here and divide by 2, and the expression inside is just a cosine of omega. So this is 1 over omega squared multiplied by 2 minus 2 cosine of omega. We could have gotten this result by just integrating over the interval from minus 1 to 1, except that in this case we will have to take care of the function changes its behavior at 0. Let me show you how we can do it in Mathematica. So the integration will involve the function 1 plus t, which applies only in the interval from minus 1 to 0, plus the function 1 minus t, which only applies on the interval from 0 to 1. I'm going to integrate in terms of t from minus 1 to 1. And just to show you that we are integrating the right function, I'm going to copy this expression and plot it, just to make sure that we're doing things correctly. So this is the function I'm integrating. The last thing I need to add to this integral is the exponential term. So minus I omega t. And voila, we get the result. The second example is a function that is a lot simpler because we already know the Fourier transform of step-like functions. So the second example, the function behaves this way. It's minus 1 from minus 1 to 0, it's 1 from 0 to 1, and it's 0 everywhere else. So if I plot this function This is how the plot of this function looks like. It's minus 1 from minus 1 to 0. Then it jumps to 1 from 0 to 1. And it's 0 everywhere else. We already know the Fourier transform of the characteristic functions. I can write g of t as the sum of two characteristic functions. It's the chi of the interval 0, 1 minus the chi function on the interval from minus 1 to 0. And I know the Fourier transform of the function chi 0, 1. It is simply 2 e to the minus I. The middle point is 1/2 times the sine b minus a over 2 is also 1/2. So it just ends up being omega over 2 divided by omega. We can rewrite it for simplicity is e to the minus I omega over 2 times sine of omega over 2 divided by omega over 2. Since g is just summation of these two characteristic functions, and those characteristic functions are symmetrical, we can write it as the Fourier transform of the chi 0, 1 minus the Fourier transform of the chi 0, 1, but with minus t plugged into it. So this is going to be e to the minus I omega over 2 times sine of omega over 2 over omega over 2 minus e to the minus I minus omega over 2 multiplied by the sine of minus omega over 2 divided by minus omega over 2. This simplifies into, I can pull sine of omega over 2 over omega over 2 outside of this expression because the last fraction, the minus sign, cancel out since sine is the odd function. So what's left is e to the minus I omega over 2 minus e to the I omega over 2. Dividing by 2, we'll have to bring the factor 2 outside. Dividing by I, we'll have to multiply by I on the outside. And if I want to switch the positions of the exponential terms, I will have to add a minus sign and make it this way. So this is going to be minus 2i multiplied by sine of omega over 2 over omega over 2 times yet another sine of omega over 2. Let's verify these calculations with Mathematica. So what we have here is a function that's negative unit step applied at -1 plus 2 unit steps applied at t equals 0 minus 1 unit step applied at t equals 1. You might be wondering, why is the formula different? Well, because we have a sine squared in the formula that we obtained, and sine squared can be written as 1 minus cosine of 2 theta over 2. And since theta was omega over 2, it changes into 1 minus cosine of omega over 2. So in fact the two expressions, the one that we get with Mathematica and the expression I got by hand, are equivalent. And again, just to confirm that the function that I'm integrating against the exponential term is exactly the function that I described, Let me just quickly reiterate what we did today. We defined the Fourier transform, we looked at few of its properties, and we looked at we realized that it's very similar to the Laplace transform. But because the determinant exponential function is minus I omega t rather than minus st, there are a few fundamental differences between the Laplace transform and the Fourier transform. For us, this is not very important. It's just yet another integral transform that can be used in a fashion similar to the fashion we use the Laplace transform for. In the next lecture, we'll continue developing the properties of the Fourier transform. Before I let you go, I'd like to mention an interesting fact pertaining to the dilations formula. When you dilate your function, when you multiply it by c, if c is greater than 1, then it has a squeezing effect on the function. When c is less than 1, it has a dilating effect on the function. If c is very large, much greater than 1, then it will result in the function being squeezed to almost a single point. And we'll see that in terms of the Laplace transform, the effect is exact opposite. The spectrum of the function, f hat of omega, is being dilated by the same factor as c. And if you studied quantum mechanics, this is exactly the math behind the Heisenberg uncertainty principle. You can determine the location of the function very precisely, which means you're squeezing the function to a tiny interval of time, but it will have an effect on the frequencies that this function bears, on the spectrum of this function. The spectrum will be very, very wide. And it is impossible to have a function that will have its spectrum and its time domain to be finite. One of those things will always have to be infinite. Either you have a finite domain for the function, an infinite domain for its spectrum, or you have a finite domain for the spectrum, only certain frequencies are present in your signal, but the signal will be infinite in time. So this is where I am going to end. Thank you for listening, and I'll see you in our next video.